Today, we'll walk through what decoding Russia's next-gen stealth aircraft countermeasures might really mean, not just in buzzwords, but in practical trade-offs, innovations, and limitations. As always, with advanced military tech, some of it is open, some speculative, but we can piece together a plausible picture and critique it. Imagine a Russian stealth fighter that's built not only to minimize its own signature, but also to actively fight off detection systems. On paper, such countermeasures would have to span 3 domains: radar, electromagnetic, infrared, thermal, and electronic warfare. So we'll run through key features in each, how they might perform, design challenges, and where the real advantages might lie. First, consider the radar or electromagnetic side. A next-gen stealth aircraft countermeasure suite would likely employ advanced radar, absorbing materials RAM that are tuned over a broader frequency range than older codings. Those codings would need to remain effective from L-band down to X or even Q bands to blunt newer wideband search radars. It might also use reconfigurable surface features or smart skin patches that can change absorption characteristics or reflectivity in real time. For example, injecting conductive fluids or using metamaterials so that the aircraft's signature adapts depending on the threat radar. That way, if a radar shifts frequency or pulse type, the aircraft can shift its absorption profile to stay stealthy. On top of that, structural shaping still matters. Canted edges, serrated paneling, internal weapons bays, recessed antennas, and masked engine inlets would all remain foundational. Performance-wise, such a system must avoid degrading aerodynamics, weight, or heat management. RAM coatings tend to incur drag, add thickness, or require cooling. The reconfigurable surfaces have to survive high speeds, thermal stress, and maintain precise alignment. So the trade-off is balancing stealth efficacy versus maintainability, weight, and durability. In the infrared realm, countermeasures would likely center on managing the engine exhaust plume, one of the hottest and most obvious signatures. This could include mixing cool ambient air into the exhaust, employing variable geometry nozzles or infrared shrouds, and potentially active cooling or heat bleeding methods. Some technologies attempt to mask or distort the thermal signature by adding a false plume or by releasing infrared decoys or flares timed with maneuvers. To be next-gen, you might even imagine a system that dynamically shapes the thermal footprint depending on the observer angle. For example, reducing IR emissions when viewed head-on, but allowing slightly more when in a low-through sector to manage thermal loads. On the electronic warfare U side, the aircraft would likely carry a multi-mode electronic countermeasures ECM suite, perhaps in internal pods or conformal arrays rather than just external pods, which would harm stealth. Such a suite might include jamming, using direction finding and targeted signals to saturate or mask the radar detection. Deception via digital radio frequency memory DRFM systems that replay modified radar returns to confuse enemy radars, for example. False targets, ghosting. Frequency agility, so that jamming can shift across bands. Self-protect jammers to decoy incoming missiles, or even modules that present false angular or Doppler returns to mislead tracking systems. A sensor fusion system that monitors enemy radars and automatically tailors the ECM output in real time. Russia already fields systems like Kabini L175V that can disturb radar reflections, create false targets, and degrade tracking with options like sweep jamming, pulse jamming, noise jamming, and DRFM techniques. Upgraded versions use GAN-based AESA antennas for stronger, more flexible jamming output. Also, there are ground-based EEW and anti-stealth radar systems like NEBO-M that Russia is developing to detect low absorption. Simplifying the fighter's countermeasures would need to face off against those as well. From the design standpoint, you'd want tight integration such that the ECM and stealth features don't interfere with each other. For example, jamming emissions shouldn't leak out and reveal the aircraft. Thermal management is tough. Radar absorbers and ECM hardware generate heat. Power supply is non-trivial. The jamming, signal processing, and DRFM modules need substantial energy, meaning you need efficient power generation and cooling. One interesting design element might be active countermeasures. Suppose the aircraft detects that it is under radar illumination. It could dynamically adjust its surface change its orientation or flight path slightly to exploit radar nulls, engage jamming, and even emit decoy reflections, all in a coordinated package. In the best case, it could cause the enemy radar to miscalculate range, speed, or direction, giving the aircraft a margin to escape or reposition. Another unique selling point would be the idea of signature choreographing. Instead of simply minimizing a signature, the aircraft might intentionally present a deceptive signature, appear as a slower, less threatening aircraft, or present multiple ghost tracks. In effect, it could manipulate what the enemy sees to buy confusion and reaction delay on performance. The question is how well these countermeasures hold up against evolving radar and sensor systems. The aircraft might remain stealthy enough until the target is within missile launch envelope and only then switch aggressively into electronic defense. The effectiveness depends heavily on detection range, radar cross-section RCS, receiver sensitivity of opponent radar, and the jammer's effective radiated power EO. If your jamming is too weak relative to the radar, you'll be overwhelmed. If it's too strong, you risk giving away your position. The optimal point is a balance. In realistic scenarios, these countermeasures can succeed only under certain assumptions that the adversary's detection system is not too far ahead, that the enemy is not using extremely low-frequency radars, which are less susceptible to stealth, and that your own system can react fast enough. In contested airspaces, multiple radar nodes cooperating and handing off tracks among them may reduce your room to maneuver. One potential weakness is that active countermeasures are noisy. They emit signals that could themselves be detected, revealing the aircraft when the stealth envelope alone would have remained invisible. So, the system must manage when to switch from passive to active defense and ideally hide its own emissions. In comparison to older generations, the next-gen countermeasure package would be more tightly integrated, smarter, more adaptive, and more automatic. It would marry passive stealth with active deception and jamming in a dynamic fashion rather than relying solely on low observation. Its value is in forcing enemy radars and air defense networks to invest in even more complex tracking, higher sensitivity, and counter-ECM capabilities. From a marketing or strategic perspective, the selling points would be: it gives a stealth fighter better survivability in denser air defense environments. It extends the effective stealth envelope deeper into contested zones, and it raises the cost for the opponent, requiring better radars and countermeasures to defeat it. However, we should caution, real effectiveness depends not just on the countermeasures themselves, but on how well they are maintained, tested, and integrated into tactics and networks. Field experience, electronic warfare training, and real adversary testing matter enormously. It's one thing to have a system in the lab, another to use it under battle conditions. All together! A next-gen Russian stealth aircraft countermeasure suite would be a holistic system combining advanced materials, adaptive surfaces, thermal management, and intelligent It would aim not just to hide the plane, but to fight back at detection itself and to shape what the enemy sees, all while staying light, fast, and reliable.